section of a shaft and a sleeve that is going to be press fitted against the shaft. And to do so, we will start with two separate parts. We'll create them as three-dimensional solids, and then we position them using the constraints in the assembly module. So let's start with the two parts, 3D solid extrusion. The first one, we're going to call that the shaft, and the approximate size, we're going to work in inches. We're going to make them about 20, the approximate size. And then we're going to draw a circle from the center. Let's give it a dimension, keeping in mind that we're going to create interference fit. This shaft is going to be slightly larger than the diameter of the sleeve, so it's going to be 2.52 inches so far as the radius is concerned. Right? And now I'm going to create a section of the shaft, so we're going to create two lines from the center horizontal and then from the center downward, and then we're going to trim the part using this technique that is auto trim. And just to be sure, we'll dimension the radius, make sure it is 2.52 inches. We're done with this, and now we need to extrude this one. We're going to extrude the shaft by 2 inches, which is the default depth. Now, what we want to do here in this case is that we want to make sure that we know the surface that we are using for the contact. Once we assemble the surfaces during the contact process, and if the surfaces are attached together, it's going to be extremely difficult to pick the surfaces for the master-slave considerations. So we do that ahead of time. Before doing that, we're also going to partition the shaft to make sure that we can place the ring on the shaft appropriately. This is how we're going to do this. We're going to go ahead and first create what we call a datum plane, halfway between 2 points, and those 2 points are going to be the two far edges of the shaft. And then we are going to partition the cell using the datum plane. All right, so we're going to go ahead, pick the datum plane and create partition, and you're done with this one. And now I'm going to go ahead and create this outer face of this section as the surface that is going to make the contact. To do so, I'm going to open the part and the shaft and double click on the surfaces, and we're going to call that shaft surface. Continue and pick this outer face, and we'll say done. Okay, so that's what we call the shaft. And now we're going to create another part. We're going to call that one sleeve. Same routine, the solid extrusion, approximate size of 20. In this case, we're going to go ahead and create two circles that is going to be depicting the ring representation. Circle number 1 and circle number 2, and we'll dimension them appropriately. Dimension the interior one to be equal to 2.48, and dimension the outer one to be with the radius of 3.0. Okay, and we repeat the process of partitioning this to create a section of the sleeve like this, and then the horizontal line. Actually, let's take it back. Line vertically to the bottom, and then auto trim this thing like we had done before, except this thing has not been trimmed off. So we're gonna go ahead and trim it like this. and then delete these lines as well. Just to be sure, we'll dimension the radii. 2.48 is good, and 3 is also good. And the depth in this case is going to be slightly smaller, 1 inch extrusion depth. And now you notice the interior surface is going to make contact with the shaft, so we're going to go ahead and open the sleeve in this case and create a surface. We're going to call that sleeve surface. Continue and pick this surface and say done. Okay, now we're ready to introduce the material. The shaft material is going to be made of steel. The sleeve material is going to be made of a brass. So we'll go ahead and click the material. The first one is steel. We're working in the inch unit, so we're going to go ahead and give it the modulus of elasticity of 30 e to the 6 psi and a Poisson's ratio of about 0.29. Okay, and the next material is going to be brass, and mechanical properties approximately is going to be 14.1 e to the 6 psi for the modulus of elasticity and 0.31 for Poisson's ratio. And while we have the brass part, which is the sleeve, in front of us, we can go ahead and start creating 2 sections as well. So double click on the sections. Let's go ahead and call this steel section. Solid homogeneous, continue. Material, click on the arrow down and pick the steel and say OK. And another one, section would be brass section. Solid again, homogeneous, continue. Material, drop down and pick the brass and say OK. And now we assign the section to, I'm going to uncheck the create set, pick this whole brass part, which is the sleeve, and assign the section that we're going to call brass section to this thing, right? And notice the part is set to sleeve. I'm going to simply switch that to shaft and assign the section by drag selecting the whole thing and say done. And the section is going to be the steel section. So we created the sections. Now we're ready to assemble the parts. The way we do that is double click on the instances, and the first thing I would recommend you doing is to do auto offset from other instances, so when the sections are assembled they won't be going into one another, and that way it's easier to move them away. So holding the shift key, pick the shaft and the sleeve and say OK. Now what we want to do is we want to bring them together and line them up. Notice we have a plane that we call the cut plane. This is the symmetry plane, so we want to line them up. First things first, we want to create a concentricity constraint. The last icon on the top section, create constraint, click and hold and move to the right. There's an icon called create concentric coaxial. That's a very good icon to make sure that these two items have the same center or concentricity. So we're going to pick the cylindrical or conical face of the movable instance. So we're going to pick this face, meaning the sleeve is going to move. And notice the prompt region says to select the cylindrical or conical face of the fixed instance. We're going to pick this instance. Be sure the two arrows are in the same direction. If they're not, you need to click on the flip and flip one of the arrows to make sure that they're in the same direction. Given that, now that the arrows are the same, we'll say OK. But notice where they're lining up. They're lining up in the far side. So what I want to do is I want to translate the sleeve so it'll be lining up at the tip over here. So to do so, I'm going to use the translate instance feature, pick the sleeve and say done. And very carefully, you want to pick the point over here that is lining up with the line at this end rather than the point on the sleeve. Otherwise you will move diagonally rather than straight horizontally. So I want to pick this point as the starting point and this point as the end point. And if you zoom out, you'll see they're lining up. Oh, great. And be sure to say OK to the positioning. So the positioning is done, and you're now ready to create a step for the solution. So double click on the step. This is going to be contact static. So we're going to go ahead and use static general, continue, leave this alone, go under incrementation tab, and I would suggest pick a very small increment of load such as 0.01, and the maximum I also want to make it 0.1. Leave the number of increments alone and say OK. The field output and history output should be set to output at every 1 increment, and that's the thing I would check to make sure that you get enough data point, and that is correct. And we're ready to create interaction, meaning the contact interaction. The first things first, we'll create interaction properties. So we're going to say this is contact property that I'm creating for the contact, and click on continue. We are working with the mechanicals, so the first thing is tangential behavior. In this case, I want to provide it with a coefficient of friction, so instead of frictionless, we're going to do the penalty approach and apply the coefficient of friction of, let's say, 0.05 as the steel to brass coefficient of friction, and then do mechanical, normal behavior, and set everything as the default and say OK. And now we're going to go under interactions. Interactions is going to be surface to surface contact, which is the default, and we're going to go ahead and say contact definition and continue. Now this is where the selection of the surfaces ahead of time is going to come in handy. Notice these are lining up together and it is hard for you to select the surfaces. Instead, if you look to the right hand side of the prompt region, you notice the surfaces. Click on the surfaces. You want the master to be perhaps the shaft one, because this is the harder of the two, and you can do highlight selection in the viewport to highlight that one and say continue. For the slave, you pick the surface region again and pick the sleeve as the surface and say continue as well. Leave everything here alone, except be sure the contact interaction property is set to what you had created. And then, since we are going to say that initially we have interference, click on the interference fit and pick the second radio button that is called gradually move slave node over closure during the step, and leave it as automatic shrink fit for the time being and say OK and OK, and now you've created the contact. Now typically when you create contact, you will see the yellow squares showing up, except that the surfaces are hidden in this case and we cannot see that very well. In case you're interested in seeing it, if you go to the wireframe representation of the model, you can see those yellow squares. So we're going to go back to the solid representation. The boundary conditions are going to be interesting. They're going to be practically just symmetric boundary conditions or cut boundary conditions. So first boundary condition, I'm going to go displacement rotation and say Z sim. That's the symmetric boundary conditions with respect to the z-axis, and we pick the surfaces that we need to pick. So let me go ahead and close that and start again. Boundary condition, displacement rotation, z sim, continue, pick this face, and also holding the shift key, pick the sleeve face along the z direction and say done. Simply restrain U3. All right, and we're going to do the same thing to the top face. So double click on the boundary condition, and we're going to call that one, being along y direction, ysim. Continue, and be sure to pick all the faces corresponding to that, and that's going to be U2 fixed. And finally rotate the image so you can apply the symmetry along the x direction. So this is going to be xsim for the boundary condition. We'll say continue, pick all of those faces again, and U1 is set to be equal to 0. You've set the boundary condition. You don't need to apply the load. Load is coming from relaxing the interference, and that's where the contact pressure is going to develop. So the last thing we need to do is create the mesh. So we'll switch to the meshing task and pick the two parts. The first part is going to be the shaft. You notice it is automatically highlighted in green, meaning you're capable of doing the sweep mesh of this part. So I'm going to go ahead and assign element type to the whole thing, and it is set for linear hexahedron. I'm going to uncheck reduced integration and say OK, and then go ahead and assign mesh control. Again, select the whole thing. It is structured, or you can do the sweep meshing, either one. Structured is fine. We'll say OK. The approximate size, if you say apply, you notice it's a reasonably coarse mesh that is hard to get a good result from, but nonetheless you can start with that and say OK, mesh the part, and you're good to go in this case. All right, so you've created the mesh for this thing, and now you're ready to mesh the other part, which is going to be the sleeve. We'll do the same thing. 3D stress hexahedron, uncheck reduced integration. We'll say OK, and we're going to go ahead and assign mesh control, which is structured, and then try to see what the mesh is. 0.42. Remember the previous one was 0.36. We're going to repeat the same process and mesh this part as well. Okay, so this is a reasonably coarse mesh. I'm going to refine that a little bit more. So instead of 0.36, I'm going to make that 0.25, and automatically delete the meshes and mesh the part, and you have 128 elements. Now if you click on the assembly, you should be able to see the two separate meshes that have come together. Now this mesh is reasonably coarse, so accurate results should not be expected from this model, but we'll go ahead and run that and see what happens, and we'll analyze the system. So we're going to go ahead and create a job. We're going to call that something. And simply submit this thing, and then we're going to monitor the work to be sure there's no errors or warnings that are of issues. Seems like this thing is rapidly converging toward the solution. It is done. We're going to dismiss and right click on the job and say results. Now if you look at the deformed shape, you'll see something very interesting. The two have separated from one another. This is simply an artifact of the scaling of the post-processor. What we're really interested in this case would be, instead of the von Mises stress, would be contact pressure, and that would be C press is what you want to look at. And if you look at the C press, it's kind of hard to get a good view because the two models are so close together. One technique that you can use to take advantage of separating the results for each part is to create a group, or what we call the display group. So the icon here is create this display group, or you can go from the tools menu and display group and say create. And in this case, since we've created the surfaces, we're going to pick the selection to be the surface. And let's go ahead and pick the shaft being the surface that we're going to look at, and replace the current drawing with the shaft. You see what happened? Now you can easily view the system. One thing you will notice, discontinuity of the contact pressure throughout. This should be a clear indication to you that the system has not behaved properly. The contact pressure is not doing well, probably because the contact hasn't taken place quite well across all the surface due to the normals that are being projected from the master toward the slave components of the surfaces. So that means one of two things. The course is really the mesh is really coarse, or the element type that you selected is not suitable. In this case, you can say with confidence the mesh is extremely coarse, and you should try to modify the mesh. So I'm going to try to do that in the next portion of the analysis. Okay, we now attempt to refine the mesh, and I'm going to switch to the mesh and select the part. This time I'm going to do something completely different. Please keep in mind this is going to increase the number of nodes, and as a result you may not be able to run that in the student edition of Abaqus. You need either the teaching edition or the full research edition of Abaqus to run it. So we're going to go ahead and click on the assign element type, drag and select the whole thing, and I'm going to switch to quadratic tetrahedron element C3D10 and say OK, and switch the mesh control as well to tetrahedron. That should be automatically switched to the free meshing. We'll say OK. Be sure to say yes, automatically delete the meshes. And now we'll see what the mesh is going to look like. This is reasonably coarse, so I'm going to say 0.2 and say OK and mesh the part. And you notice I have about 11,000 elements that is generated in this case. And if I were to switch back to the assembly, you notice how this is going to look like. I'm going to refine the mesh of the sleeve as well. Leave it as hexahedron, except that seating the part is going to be perhaps 0.12. And once again, you say automatically delete the meshes and mesh the part. Excuse me, mesh the part. Yes. And you're looking at the assembly. Well, yeah, it should look a lot more reasonable. We're ready to go ahead and submit the job and say OK and monitor the work and double check again, be sure there's no errors or warnings that appear. And seems like everything is starting out okay. We take a look at the iterations and possibility of severe discontinuity and how many iterations it takes for it to resolve this thing. Yeah, the first increment of an interference fit always going to be the most challenging one for the equilibrium iteration. After that, it seems to go pretty much smoothly. You notice the time step and the time increment is also steadily increasing, meaning the program is having an easier time converging toward the solution. As a result, it is increasing the increment. You notice you specified that the maximum increment is going to be 0.1. So you should see the time increment at some point reaching 0.1 and then staying at 0.1, except for the last increment that would be the difference between the total time and the value that was prior to that. as I mentioned, you notice the point 1 has been reached. Now if you're brave enough, you can make the maximum increment to be quite a bit larger than that. I don't recommend it unless you have an extremely large problem and you want to save some time and you're sure that your contact is fairly easy to maintain and easy to converge. So you notice the last time is 0.9178. We said 1.0. Whatever the difference is going to be the last increment. The solution is complete. We'll go ahead and initiate the results. And once again, take a look at the deformed shape. By now you should see it is looking a lot easier so far as the convergence is concerned. And I'm going to go ahead and switch to contact pressure. And by a cursory observation, you notice the uniformity throughout the system. And we're going to go ahead and do our group, create display group, pick the surfaces, and pick the shaft surface and say replace. And this is what I mean by uniformity of the contact pressure. The only thing that you need to pay attention to is that where the edge of the sleeve has left the shaft, meaning there's no more sleeve on the other side of the shaft, that's where you're going to have inherent stress raisers, where you're going to have artificially high stress value. If I were to switch back to the replace all, this is what I'm talking about. See, now there is no material after this, and as a result you have a severe discontinuity of stress on the shaft, and you will have something similar to that on the sleeve. If you were to go and do a display group and pick the sleeve surface instead and say replace, you'll see the same thing over here. So I'm going to go ahead and do a plot, XY plot, and this display group is an easier way for me to pick the nodes that I want to plot. So let's go ahead and pick the shaft surface again and replace that. And I'm going to go ahead and close this up and go to under tools. I'm going to create a path along the edge, so it's going to be path, create, and carefully zooming in starting from one end. I'm going to pick the node list, and let's call that the shaft edge nodes, and continue. And you can either pick add before or add after. I always pick add before. And now I'm going to pick the nodes, holding the shift key. Be sure to pick the center node because the 10 node TET has the mid-side nodes. So I'm going to continue selecting this, except that I don't want to pick that last one, since I know that's discontinuity over here. I don't want to pick that one, pick this one instead, and that's where I'm going to end. Now you notice you have the discrete number of points, so your plot is not going to look very impressive. However, one note of caution for you is that for you to be able to plot anything, you need to move away from the surface display, because the program does not have any results associated with the surfaces. So I'm going to do replace all, and now I'm going to go ahead and go to XY plot, create XY data for the path, and continue. And you notice the path is the only one that we had, so it automatically picks the elements corresponding to that path, and the contact pressure is the field output. I'm going to simply click on the plot. This shows the variation of the contact pressure as a function of the distance along the path. Now don't be too scared. Notice the scale. We're going from anywhere from the 36.5 to about 40,000 psi, so the difference is about 10% from the minimum to the maximum, and that's what you're looking at so far as the variation of contact pressure. In reality, your expectation is that there shouldn't be any sort of a variation. These are going to be inherent artifacts of the meshing and the contact algorithm, and you can refine the mesh even more to smooth this thing out. All right, so finally, looking at the deformed shape, for those of you who are still baffled about the separation of the two, if you were to go back to the common options and the deformation scale, notice what it is set for, pick the uniform and set the value to 1, meaning you're looking at a 1-to-1. Now you do see the correct rendition of how these are supposed to be contacting. And if you want to impress